Hello and welcome back to Chapter 15. We're covering waves and the anatomy of waves, shoreline erosion, sediment transport, and then engineered structures. We're getting closer and closer to the end of this chapter. We'll wrap up with some different kinds of coastlines and coastline processes. In general, we know a little bit about waves and wave anatomy already from talking about the geophysics of the Earth's interior, the geophysics of the Earth, and we know that waves have heights and widths and lengths and amplitudes. And what we're interested in is really sort of how the sun here is going to generate energy in the form of wind through differential heating, and that wind is going to create waves, and those waves are going to transmit that energy as far as they can, which eventually is to reach the Earth, the continental shore, and then what happens at the shoreline to that sediment. In general, we have mechanical forces that are going to be basically putting a mass. Water is fairly heavy, so you hit something with something heavy and it can break apart. So we have mechanical forces, just the weight of the water on the rock can break it up. We've got hydraulic pressure. So this would be like equivalent to putting your thumb over the end of a garden hose and restricting the size of the volume of water that can come out at a given time. It increases the pressure and squirts the water a greater distance. Water that's hurled against rock will find its way into cracks, and that will help to increase the pressure in those cracks and push the rock apart. The other thing that can happen is that sand tied up or in the currents themselves or in the waves can actually break apart through grinding and abrasion as well. And then, of course, you have dissolution going on where rocks may react with ocean water and actually turn into ions. All those are going to work to break apart rock along the ocean's coastlines. The wave itself is constructed with the highs above mean sea level, and we've talked about tides already, and the lows, which are sort of below mean sea level. And the wave depth is a function of the wave length. The wave length can be measured in meters or feet, from feet or meters from crest to crest or from trough to trough, so it doesn't really matter. And then we have the wave height, which is the base of the trough to the height of the crest, and that basically defines our waves. And we talked a little bit about how waves will have different periods, so that's the time it takes for one wave to pass a point, and they can also have different frequencies, so that's waves per second, which is also known as hertz. So we can measure the periods of the waves as well. The waves don't extend, surface waves caused by wind don't extend very deep into the ocean. Wavelengths here or the depth, I should say, of a particular wave is 1/2 of the wavelength. So if this is the wavelength, then this distance should be the wave depth. And so if you have swells that are coming in, with wavelengths of, let's say, 100 meters or something, then you're only going to have waves interacting in the surface down to 50 meters. But oftentimes it's even much, much lower than that in terms of wave depth. In general, wave behavior, waves don't actually move particles in a way that you might think that they do. If you were, say, a rubber ducky, right, and you're sitting on the ocean surface, and we'll just erase some of these guys here. You're sitting on the ocean surface, and you're sitting out here. There's our duck. It's at a peak here, and as the wave moves through the system, the duck's going to move down, and then it's going to move back up, and then it's going to move down. It's not going to move to the left or to the right. Okay, so waves don't really do a lot of particle motion or create a lot of particle motion. They create a little bit of particle motion out in the ocean, but it's really currents, right? And we've talked about currents that are pushed, so we're pushing water with wind, or we're displacing water from one location and has to rise back up in another location. That's the kind of thing that's moving mass in the ocean. Waves are energy that are being transmitted through the ocean, which is slightly different, right? Now, technically, if we go and get into the nitty-gritty of this, yes, there is some motion associated with waves, but mainly it's currents that move things. As those waves approach the shore, what's going to happen to them is a couple of things. One is that the base of the wave, which I'm drawing a little box around down here, the base of the wave is going to hit the ocean bottom, and it's going to start to slow down. So we're going to slow the wave down as it drags along the ocean bottom. And then what's going to happen as the velocity of the wave decreases, its amplitude is going to increase. So we're going to slow the wave, and its amplitude is going to begin to grow. And as it does this, it's going to get tall. And as it gets taller and gets a little bit slower, it's going to become unstable until we get to the point where we get what's called a breaker. And the breaker is where the wave is literally just falling over. All right, that's all that's happening is this high amplitude wave is toppling over because its base is moving much slower than the top of the wave, and that's what creates those sort of curled waves that we see guys surfing in. You can see them in Lake Michigan even too, although they're a lot smaller. When the wave breaks, we're going to get some kinds of behavior as well along the shore, and I'll talk about that in a minute. But the slowing of the wave along the ocean floor creates a kind of what's called wave refraction, or a bending of the wave. So if I draw a line along the crest of these waves out here, it hits this boundary, and then it turns and changes direction. It's bent. That's just like light passing through a prism or from one medium to the next. It's going to come along, and then it's going to be bent. And so waves are going to be moving more slowly near shore, and that bend is going to bend them in towards shore, and that is called wave refraction. The angle at which the waves come in, they usually don't come in straight. They come in along a curved path, or a refracted path, if you will, and that is going to be like the bristles of a broom, and it's going to generate a current along the shore called longshore current. Longshore current occurs within that surf zone, so where you've got the waves breaking, and it's going to pull along sediments along with the water. And so longshore current results in this word up here at the top of this slide, longshore drift. Longshore drift is the movement of sediments. So because the waves come in at an angle, they drag the sediments along the shoreline and create longshore drift. Now, there's another way in which sediments can move, and that has to do with how we see the waves swash up and then swash back. I'm drawing this down here in the bottom right-hand corner. When a wave comes in, it comes in at an angle like this, and it hits the shoreline and washes up. But when gravity pulls it back the water off the shore and back out into the ocean, it pulls it down straight. And so it comes up at an angle and comes back straight, and up at an angle and back straight. Well, or so perpendicular to the shoreline, if you want. Up at an angle, back perpendicular to the shoreline, up at an angle, back perpendicular to the shoreline. Anyway, this goes on and on and on, and what it has the effect of doing is washing sediments up and back, up and back, up and back, all along the shore. So you really have two kind of ways of moving grains. One is within this longshore current, which is just offshore in the surf zone, pulling sediments along, and the other is actually up on the beach face or along the beach within the swash zone. Okay? The effect of moving all these sediments is that we create structures wherever there are sediments to be moved. So if there's a sufficient sediment supply, one option is that we can create a spit, and a spit is a finger of sand that comes out along the shoreline and partially covers an embayment or a bay. The spit actually points in the direction of longshore current. So if you come to the figure on the right here, longshore current is kind of like in this direction from right to left in this diagram. The other thing that can happen is if you have enough sediment, the sediment zone will cover up the whole bay, and that's called a bay mouth bar, and it creates a kind of little estuary back there, a little swampy wet zone that's sort of classically has different kinds of plants and organisms that are basically protected from the more energetic waves that might be coming into the region, and so you get a little change in ecosystem back there. Okay. The movement of sediment is a problem, and it's not unnatural. But if you build a house, typically you want the beach to stay in one location, and it turns out that within a few years you might actually see the beach in front of your house move. So this problem of moving the sediments is actually pretty fast acting, and becomes an immediate problem if you're owning a piece of property that once had a beach associated with it. We do try to control longshore drift, and we do it with three main structures. Those structures are jetties, which are parallel to channels, and those are shown up here on the top figure. Jetties coming out here, and there's a jetty here. And the idea is that they keep all of this sand that's on the left-hand side from moving out and around into this channel. So they protect the channel and allow us to move in and out. Now, what happens is that on the up current, we'll call this the up current side. On the up current side, we build up sand, we build up the beach, but on the down current, which is over here, down current side, okay, we erode the beach. So notice how much thicker the beach is on the left side of this image and how much thinner it is, right? Most of this is water out here on the right-hand side of the image. We also do this kind of thing if we want to sort of stockpile sand in front of homes. And so we call these groins. Groins are very much similar to jetties. They come out and are perpendicular to the shoreline, but you'll notice up current of the groin, we find a thick beach, and down current we find a thin beach. So this is up current, and that's longshore current, and this is down current. And so that means that we see sediments being transported parallel to the coast, and we can use these as a way to determine the direction of movement. The third thing we do sometimes is to put in what's called a breakwater, and the breakwater is shown down here at the bottom. Here it is. It is, as one might expect, if we have everything perpendicular to the shore, now we're going to just turn something sideways and have it be parallel to the shore. So the breakwater is parallel to the shore. And what it tends to do is it tends to cause waves to get bent around and to come around like this. So the breakwater actually deflects waves around it and sort of brings them towards each other. Now, what that has the effect of doing is building out the sediments towards the breakwater. So the breakwater brings sediments around and then builds that action of longshore current and swashing and so on. Will actually build the sediments out behind the breakwater, so the sediment load gets thicker there. But of course, then in this area to the right of the breakwater and this area to the left of the breakwater, you might expect actually to find zones of more intense erosion. So none of these things actually really solve the problem. Here's breakwaters along the Jersey shore. So there's a breakwater, there's a breakwater, there's a breakwater, and so the wave energy is deflected. Or bent or refracted, if you will, and bent around these, and then scooches in towards the center like this, and towards the center, and builds out the wave, the beach toward the breakwater. And so the problem is that we can't stop the movement of sediment. The movement of sediment is natural. It is not an unnatural thing. It has little to do with what we've done in terms of construction. But we often have to just bring sand back to the beaches because the supply of sand is too small to keep up with the the wave action, the longshore current, and the swashing. Now, why is that? I mean, that doesn't necessarily make sense if it's a natural process. And the answer has a lot to do with the fact that we've dammed up many of the rivers and streams in this country to provide hydroelectric power and to provide reservoirs. Well, sediments that are coming down from mountainous regions or across the country will deposit their sediment, rivers and streams will deposit their sediments in these reservoirs, which will eventually silt up or fill up. Now, this is a natural process. I mean, most lakes will eventually fill up with sediments if you give them tens of thousands of years to do so. But by creating these reservoirs, we actually block that material from getting out to the shore, and that's the primary source of sand and sediment. Sometimes it can be made at the shoreline. This is not uncommon, especially in small islands and places where you have coral reefs and high energy systems. But for the most part, a lot of the sand and sediment is brought from rivers and streams. It's not formed in situ, and because we've gone to the extent of we've gone to the rivers and streams to use them as resources, we've blocked much of that sediment from reaching the shoreline, and that means we've actually enhanced the erosion problem by shutting down the sediment supply. So that kind of wraps up our discussion of waves along the shore, the development of local currents. There are other kinds of currents like rip currents to talk about too, as well as features that we might use to manipulate or to stall or to slow down the process of sedimentary erosion. We'll move on to talk about the different types of coastlines as the last part of this lecture.